Okay, welcome everyone, and let's jump into the quiz. Okay, so here's the quiz. Hopefully you can see it. It's not showing me. Oh, there it goes. Now it's showing me. You can see it. Okay, so we want to convert 2x squared plus y squared equals 1 to an equation involving polar coordinates. And then be sure to write r as a function of theta. So I'm going to do the following. I'm gonna rewrite it in the equation mode because this is one of those where I think it helps to think about it as an equation and write it as an equation. So let's do that. There it is. So we have 2x squared plus y squared equals 1. And we want to look at that. And the question I've got for y'all is what could I do to make this a lot prettier? There's something in the way here that if it wasn't there, it would be a lot better. What do you see?
The 2?
The 2. So here's what I like to do. Just get rid of the 2. Sound good? Can I do that? What do you think?
Wouldn't you just have to divide it by 2?
You can divide by 2, but the problem with dividing by 2 is then you're going to have a y squared over 2 and a 1/2. But here's what we can do. So you can't just get rid of the 2. You can't just erase the 2. But what you can do is say, well, I got rid of an x squared, so let's add an x squared. Now you agree that we're allowed to do that? Any questions so far? Okay. So now what we can do is we can say, what is x squared plus y squared? That was the whole point. What's x squared plus y squared? Hopefully you have that memorized. Yeah, that's r squared. And then we're going to have a plus, and then we have x squared. Well, do you remember what x is? Yeah, r cosine theta. So x squared is r squared cosine of theta. So I figured on this one I'd make it prettier because it's easier to see. Cos squared of theta. There we go. And then equals 1. Any questions so far? Okay, now what I need to do is I need to solve for r. And hopefully that's not that big a deal. I could factor out an r and get r squared times 1 minus the cosine squared, or 1 plus cosine squared theta. Equals 1. And then my last 2 steps, let me pop this in so it's readable. And then my last 2 steps are to just divide by the 1 plus cosine squared theta and take a square root. And when we do that, we get r is equal to 1 over, let's see, we have 1 with a square root, because we got to take the square root of 1 over 1 plus the cosine squared theta. Any questions on working this out? Okay, there are other ways of doing it, but I think that's the easiest. Maybe you don't agree, but I think it's the easiest. Always look to see what's easy and see if you can write it in the way that's easy and then do the problem. That's always a good math technique. Any questions at all on question number 1? Any questions on this? Okay, so now let's go to question number 2. Okay, question 2 is supposed to be pretty quick and easy. The point P in polar coordinates is given by P equals 4 pi over 3. Write the rectangular coordinates for this point. Okay, so we need to find out what x and y are. And hopefully you have the equations memorized because that is important. They're not that hard. How do we get x? Yeah, r cosine theta. So let's, I think I want to do this one in equation mode because otherwise there's going to be too many PIs and stuff like that. So we could say x is equal to r was 4 times the cosine of theta was pi over 3. And what is 4 times the cosine of theta of pi over 3? Yeah, so cosine of pi over 3 is 1/2. So 4 cosine pi over 3 is 2. And then we got to get y. Y is equal to, and what's the formula for y? Yeah, r sine theta. So r was, again, is equal to 4 sine of pi over 3. And 4 sine of pi over 3, not quite as nice, but not too bad. What's 4 sine pi over 3? Yeah, 2 root 3. 2 times the square root. I think it's basic. There it is, of 3. So our final answer is the point 2 comma 2 times the square root of 3. And there's our rectangular coordinate way of writing the point that is written in polar coordinates 4 comma pi over 3. Any questions at all on question number 2 or about the quiz? Any questions? Okay, if there's no questions, I'm going to share my desktop again. And let me ask you, do you have any questions about homework or anything else? Any questions? It's a good time to ask. Y'all found it easy? Okay, if there are no questions, we can move on. But I want to make this big announcement. So I just want to let you know that there's the Math 119 class, and that's not like any other math class you've taken, I promise, because it's a class on watching the conference, going to the conference. You don't normally, I'd say going to the conference, but everything's stupid and weird now, and we're all online, and you can't actually go to a conference anymore. Now you just log into a conference. But if you want, it's like, I promise you, it'll be the easiest math unit you've ever gotten. Is all you have to do is log in. There's no final exam at the end, anything like that. It is a week from Saturday, and it is a few talks on some cool things you can do. In fact, maybe I'll pop it in. So just note that there's a few things. One is the first 2 pieces are just some kind of math tools. And then the keynote speaker is gerrymandering. So it's actually really neat mathematics. I've been involved in it in the positive way, by the way, on trying to deal with the best way of making voting happen, in America. I was personally involved in the county, but in America, how do you make voting happen? And it turns out that there's lots of choices and everyone has issues. There's no perfect voting way, and it's all mathematics and stuff that you should be able to understand. That's the cool thing. And then the next speaker is on a journey through mathematical time. So kind of cool stuff. So quantum computing, kind of math history, all kinds of fun stuff. And like I said, all you have to do is watch it. And it's a good experience because you get to kind of see what happens, in kind of the higher level, even though it's not going to be higher level math. It's going to be the feel of that. But I'll let you know, if you don't register very soon for the class will cancel because we only have 2 students right now. So the only absolute requirement is that on the 24th of April, you have to log in and be there. Not be there, you have to be at your computer. Okay, there's even a game because I'm leading it, and that is the casino style online games. And you might have an advantage because we live in Tahoe. So just note, and again, if enough sign up for it, it'll go, otherwise it'll get canceled. So I figured I should mention it. So if there's any questions about that, I can answer. If not, how do we sign up? Okay, so there's 2 things you'll need to do. The first thing you'll need to do is go to Lake Tahoe Community College, just like you signed up for this class. You sign up for that class. So in the schedule, let me just show you. When's the sign up date by? Here's the issue, is the administration is going to cancel the class if enough people don't sign up. When they decide to cancel, I don't know. So it's not the last chance for you to sign up as a student, but the last chance because the administration will decide to cancel and then you can't sign up if the class gets canceled. So just a note. So anyhow, let's see, academics. In here somewhere, schedule classes. It's always hard with Zoom. I have to move things around. And then spring schedule. In a moment, scroll up a whole bunch. You can either scroll in a different way to go faster. Just got to move all this other stuff on Zoom. Here we go. And you'll see Math 119. The Friday's been, we're not doing the Friday because this was when we thought we might have it face-to-face. And so we decided with the online, it's going to go, and it won't quite go to 5:45, but it wasn't really worth changing the schedule. So just note it goes from 9 till around 2, might be 2:15. So hopefully that answers you the questions. But again, like I said, if you want to sign up, you should sign up soon. It's just a unit half unit, which means it doesn't cost much money. And then once you do that, I'll let you know how to sign up for the conference instead of the class. Because first you sign up for the class, then you sign up for the conference. And it's all free, by the way. The conference is free. Any other questions? Okay, let's go back to a little bit of math. And again, let me give you one last chance if there's any questions, since no one had any about the like homework and stuff. If you don't, then I'll move on. Okay, so let's talk about polar area. So I thought it might be kind of interesting to kind of show you what it might look like, and then realize that there's stuff to do. So let's go to Desmos. And how about just sine of 6 theta? Oops, r equals sine 6 theta. Okay, so beautiful flower. What if you wanted to say, find out what is the area of this flower? Okay. If, by the way, if you wanted to convert this to rectangular coordinates and then use integration to find the area of this flower, you'd be crying. Doesn't it look horrible? Okay, so just let you know, that's not the way you want to do this one. Okay, but we want to find out the area of the flower. Now, as you can maybe see, otherwise you can prove it without too much difficulty, the flower has many petals, and each petal has the same area. So one thing you can note is that you can count the petals, and there's 12 petals. So if you can find the area of one of the petals, then you can find the whole area by multiplying by 12. Any questions on that idea? Okay, so that's our goal, is to say, how do we find the area of something like this without having to turn it into rectangular coordinates? Would be a complete nightmare. Trust me, that's not what you want to do. So any questions on our goal before we get into it? Okay, well, the way you did area last quarter is you cut this into a bunch of rectangles at the very first day of last quarter with Bruce, is you cut it in a bunch of rectangles, and then you added up all the rectangles. You took a limit as the number of rectangles went to infinity, and that would give you the area. Any questions on that? Okay, the problem is you don't want to use vertical rectangles, because what a vertical rectangle is, it's saying we're going to move X a little bit, and we're going to move Y a little bit, and we're going to find that rectangle. Does that make sense? And the problem with that is X and Y are irrelevant in polar coordinates. What do we want instead of moving X and Y a little bit? Any thoughts? Or we want to move X a little bit and then just let, watch what happens. So instead of moving X and then finding the area of the rectangle, what are we going to move now? What's our variable here? Yeah, we're going to move theta. Okay, theta is the independent variable. So we're going to move theta, and we're going to say that if you start with a theta, like that goes to here maybe, and then you increase that theta by a little bit up to here, then you're going to get a region. It won't be a rectangle, because you have a theta, and then you move theta out here, and you're going to get some interesting piece, and it'll be like a little piece of a circle, because we're going to fix our R, because that's what you do when you did rectangles, is you fixed your Y, you moved X a little bit, and you drew a rectangle. Now we're going to fix our R, we're going to move our theta a little bit, and we're going to get a little arc of a circle. Okay, any questions on that? All right, so that's the idea, but here's the thing. How many of you remember what the formula is for a little piece of a circle for the area? And my guess is none of you, but I might be wrong. You probably remember the area of the whole circle, but what about a little wedge of the circle? It's a little bit messier. And that's what we want to do next, is we want to talk about how do you get that area of that little piece of the circle. So let me give you some reminders. So I hope you all remember that the area of a circle, a whole circle, is pi r squared. Okay, I'm hoping that is like ingrained in your brains, is it? Okay, and I'm also hoping, also should be in your brains, maybe not quite as loudly, but still should be in your brains, that the circumference of a circle is 2 pi r. Hopefully that's another one that you remember really, really, really well, because that happens a lot and you've known it since you were, you know, maybe middle school. Any questions so far? Okay, so then what we're going to do is we're going to say, well, let's say instead of having the whole circle, let's suppose you have a piece of a circle. So again, now we're just going to go, we're going to have a little bit of a theta of a circle. So instead of going all the way around, how far around is it? How many radians around a whole circle? Yeah, 2 pi radians. So there's 2 pi radians around a whole circle. So if you've only gone theta radians around the circle, then we've gone theta over 2 pi as a ratio. Any questions on that? So the ratio of the circumference should be equal to the ratio of the area. So what we can say is theta is to 2 pi. So in other words, the circumference of the little piece of a circle, which means you've moved theta, over the circumference of the whole circle should be equal to the area of the little piece of the circle divided by the area of the whole circle. So theta over 2 pi equals a over pi r squared. Have I lost anyone in that idea? Is that clear? Okay, so the nice thing is the rest is very easy math. Okay, this piece, to come up with the idea that that's what we need, that's hard. But the rest is easy. Now we just do basic algebra. We cross multiply. And if you cross multiply, you get theta times pi r squared, or pi r squared theta. And you get 2 pi times a. So we know that pi r squared theta equals 2 pi a. And then what we can do is we can solve for a. So if you divide by 2 pi, the pi's cancel. We get a 2 in the denominator, pull it out as a 1/2. And then typically you switch the theta and the r squared, and you get area equals 1/2 theta times r squared. Any questions at all on this formulation, this derivation, to find the area of a piece of a circle that has moved theta radians? Okay, because that's going to be the main equation that we're going to use to be able to handle area, because we want the area. Now we can cut our region into little tiny delta theta pieces. So the idea is if you cut it into tiny delta theta pieces, then the theta becomes a delta theta. Okay, which just means that instead of saying I've moved all of theta around, I'm going to just say, well, theta is really small, so I've moved delta theta around. All I've done is changing the letter's name. Any questions on that idea? Okay, and by the way, here's a picture. And that is, we have our whole circle. We have a piece of a circle, a wedge. And if the angle of the wedge is theta, then the area of that wedge is 1/2 theta r squared. Okay, and by the way, if theta was 2 pi, then you'd end up with pi r squared just like you'd like it to be. And it better be, right? So if you go around the whole circle, it better be 2 pi r squared for the area. Anyone lost on what I just did? A little geometry here. Any questions? Okay, so now what we can do is, again, we can treat theta as a tiny little theta instead of a big theta. And if you treat it as a tiny little theta, then that means A is going to be tiny also. And we can say dA equals 1/2 r squared d theta. Anyone, any confusion? Is that totally clear on how this works? Okay, and now all of a sudden, instead of looking like geometry, what does this equation look like? Instead of the class of geometry, what class does this one look like? Here's a hint. What's the name of this class? Yeah, this looks like calculus. Okay, that's the whole point, is we want to do some calculus. We want to find out what the area of the circle is, of the polar region is, and this is how we do it. So then what you should be used to in calculus, once you have something like this, what do we put on the left side of both of these equations? Of both of the pieces? What do you put on the left of each side? So that it looks even more like calculus. What's it missing? Yeah, so it's missing an integral sign. What's the integral of dA? Very easy. A. So what we could say, this is the big theorem, and I just proved it. And that is the area of the polar region bounded by r equals r of theta for theta between A and B, lowercase a and lowercase b, by the way, is given by area equals 1/2 the integral from A to B of r squared of theta d theta. So I made it look a little fancier instead of just r squared of r squared of theta, because remember, r is a function of theta. So this is just emphasizing that r is a function of theta. And I pulled the 1/2 out. You're always allowed to do that with integrals. So that is the big theorem for polar coordinates and area. Any questions on this idea? Okay, where do you think this is going to get hard? When you have multiple functions, that could be hard. Finding what to pick for theta. Theta is just theta. But maybe you mean this, because this is where what's hard, is not what do you pick for theta, but finding A and B. Typically, finding A and B could be one of the hard parts. And then the other part, if you have to do it by hand, as always, is integrating. There may be some like evil integration tricks with, who knows, inverse trig sub or some miserable kind of thing you have to do. But finding A and B is a new hard piece, whereas in the old days, that was almost never hard, finding A and B. Any questions at all on the theorem? Any questions? Okay, so the idea is we should know how to use it. So here's an example. Okay, I think maybe I'll do the one we did. Make it a 6. Okay, so the question is, find the area of one petal of the flower r equals sine of 6 theta. Okay, and we saw, here's our picture. So we got the sine of 6 theta, and we want the area of this petal right here. And again, once you get the area of one petal, multiply by 12, and you get the whole flower. Any questions on the question? Okay, so what we need to do, as I mentioned, our first step is to figure out what A and B are. Any questions on that idea? Are A and B 0 and 2 pi? Because that goes, that'll, you know, theta goes from 0 to 2 pi is as far as you could ever go, right? You think A and B are 0 and 2 pi? Yeah, definitely not. Definitely not. Okay, so 0 to 2 pi does not work. What we need is a single petal, not like a whole bunch of things. So we need to go and figure out what the angle is when you get back to the origin. So that's what we go do next. Okay, and this is where for some people have a lot of trouble because it's trig. And not everyone loves trig, but you got to do it whether you like it or not. So we know from that picture where we start and we end, what is R? Let me go back to the picture. So what is R at the beginning and end of a petal? Yeah, R is 0, because if you're at the origin, that means your radius is 0. Any questions on that idea from the picture? So we know that R is equal to 0. So now we can go ahead and we can write 0 is equal to sine of 6 theta. Okay, and now you got to remember your trig. When is a sine 0? Okay, pi over 2 is one of them. Is that the only place a sine is 0? Actually, pi over 2, it's not 0. Sometimes I get tricked into it when I read the chat box. Yeah, pi, but is that the only place? Sine of 3 pi over 2 is not 0. 0 in anywhere, any other places? How many times is the sine of an angle 0? How many angles are there that give you 0? I don't see y'all jumping in. There's an infinite number of angles that give you 0 for a sine of theta. So this is where we have to go back and remember how that works, is that the sine is 0 when theta is k pi. So in this case, not theta, but 6 theta. So 6 theta equals k pi. Any questions on that? Okay, and by the way, as usual, calculus is not the hardest part of calculus. Trig is typically harder, okay, or sometimes brutal algebra. The calculus is actually gonna be pretty easy, but you know, remembering things like 6 theta equals k pi, that's something you need to write out. Okay, so what we need is we need theta. So we can say theta is equal to k pi over 6. And let me make it bigger so you can read it. There we go. Any questions on that bit of trig there? So once we have that, now we could pick any 2 consecutive values of k, and that'll get you a petal. Do you all agree with that? So what consecutive values of k would you like to pick? I'll let you choose. Okay, 1 and 2 it is. Okay, so if we use k equals 1 and k equals 2, then we can say our area is equal to the integral If k is 1, you get pi over 6. This is going to look really small. I'll make it bigger, I promise. Pi over 6. I forgot the 1/2 outside. And then if k is 2, you get pi over 3. Oops. Try that again. There we go. We get pi over 3. And then r is sine of 6 theta. So that's going to be sine squared of 6 theta. D theta. Any questions? Any questions on this? Okay. By the way, had you chosen different consecutive values, you get the same answer. So if you chose 0 and 1, which I think would have been easier, but you chose 1 and 2 as the first choice, and I'll take the first choice, then you'll get the same answer. Had you chosen 141 and 142, you get the same answer. Okay, so because each of the petals has the same area. Okay, I don't know if I'm going to waste your time unless you want me to integrate this. So you can use the half angle formula. Is probably the easiest way, and you end up with 1/4 times 1 minus the cosine of 12 theta over 2, and then integrate. But do y'all understand how to do this? Any questions at all on the process of finding the area for a polar curve? Any questions? Okay, if there's no questions, I'm going to move on to the next piece. Again, if you remember, we have a lot of topics, and we just did polar area, and now we can do polar arc length. Okay, so to talk about polar arc length, what I want to do is I want to start out with some basic trig stuff, basic polar coordinates, and hopefully you all remember that x is equal to r cosine theta and y equals r sine theta. Okay, of all things in these couple sections, number one is those equations, because that defines polar coordinates. So the first thing I want to do is just, and it's kind of an off topic, but it'll help us anyway because we need it, is if we wanted to find the slope of the tangent line to a polar curve, as in dy dx, what you can do is you can look at these polar coordinate equations and then think of theta as the variable and r as a function of theta. So that means everything to the right of the x here is only thetas because r is a function of theta. And similarly, everything to the right of the y is also a function of theta, which means you have x as a function of theta and y as a function of theta. Where have you seen something like that in this class? We've only had a week of class where you have x as a function of a variable and y as a function of the same variable. Where have we done that? The hint is we spent like most of last week doing it. Are you all paying attention? The hint is we didn't use the letter theta, we used a different letter. But it's what we spent most of last week doing. Not Friday, but all the rest. Yeah, it's like a T. So these are parametric equations. And the great thing is, if we think of this as parametric equations, we already know how to find dy dx, because dy dx is dy dt over dx dt, or in this case, dy d theta over dx d theta. And r is a function of theta. So if r is a function of theta and we want dy d theta, what we need to do is we need to use the product rule. So we can say dy dx is dy d theta, which is going to be the derivative of the first, or r prime, times the second, sine of theta, plus the first, which is r, times the derivative of the second, which is cosine theta. Let me make this a little bigger because it might be too hard for y'all to see. And similarly, dx d theta will be the derivative of the first, which is r prime, times cosine theta, plus the derivative plus the first, which is r, times the derivative of the cosine theta, which is minus sine theta. So any questions on dy dx, given that you know x and y, or you know in polar form? Something I was a little disappointed about is the book doesn't show this. And so I just couldn't resist it, because this is something that every calculus book should show. But any questions on this? Okay, and we're going to use it. Okay, at least we're going to use the top and the bottom. So now what our goal is to deal with arc length. Now, who remembers arc length with parametric equations? And remember how you found arc length given parametric equations.
You integrate the square root of x prime plus this x prime squared plus y prime squared.
Exactly. So you integrate the square root of x prime squared plus y prime squared. But the good news, and this is why I actually wrote this out, and also because I couldn't resist, is that the numerator is x prime. Is y prime, and the denominator is x prime. That's what we did, right? So this was a way of writing both of those in one shot, and I was able to show you the dy dx also at the same time. So what I can do now is we could say, what's the integral of the square root of x prime squared plus y prime squared? So I find x prime squared plus y prime squared. So, and the good news is it becomes beautiful. It's one of those really nice things. So if we take x prime squared, that's r prime cosine theta plus r sine theta, and we square that, that gives you r prime squared cosine squared plus, oh, you know what, I forgot, there's 2's there. They're going to go away, but still. Plus twice the product, so 2 r prime r cosine sine, or sine cosine. Okay, and it's a minus because there's a minus here. And then plus r squared times sine squared. Okay, that was dx d theta squared. And then we do dy d theta squared, and that's going to be y prime, that's going to be r prime squared times sine squared theta, and then plus twice the product, so 2 r prime sine theta cosine theta, when you multiply these together, and then plus the last one squared, and that's r squared cosine theta. Anyone lost on this foil? That's all I did, is I just foiled the top, the bottom and the top, and added them together. All right, well, now let's take a look. If you look at the r primes, those go away. We have a minus 2r prime sine theta cosine theta, and we have plus 2r prime sine theta cosine theta. So those are gone. If we look at the r prime squared, you get an r prime squared cosine squared plus r prime squared sine squared. What's r prime squared cosine squared theta plus r prime squared sine squared theta? The hint is it's beautiful. Yeah, it's just r prime squared because it's r prime squared times cosine squared plus sine squared. It goes away, it's just r prime squared. Similarly, I have an r squared sine, that should be squared. And that one should be squared. So we have an r prime sine squared theta plus r prime cosine squared theta. And r prime sine squared plus r squared sine squared plus r squared cosine squared is just r squared. So all of this horrible mess just becomes r prime squared plus r squared. Any questions on this derivation here? All right, so now we're ready for the big theorem, and that is the arc length of the polar curve, r equals r theta, for theta between a and b, is the integral from a to b of just the square root, and I wrote the r squared, because the way the book does it, r squared plus r prime squared d theta. It's actually kind of a nice, pretty formula compared to this messy stuff when you FOIL the thing out. Any questions on the theorem about arc length for a polar curve? All right, for this one, by the way, if you do it by hand, it's usually completely miserable. Can you imagine when you have a square root of some squares and you're adding, and it's usually really, really rough. If you do it with the computer, then what do you think the hardest part might be sometimes? Not in this, not in all examples, but maybe this one. Any thoughts? Yeah, finding A and B. Okay, again, that is, my experience, grading tests and stuff, that's usually where people stumble. So let's do an example. And of course, in this example, we're going to find A and B. Okay, and the rest is basic if you use a computer. Set up the integral that gives the arc length of the curve, r equals 1 plus cosine theta. Okay, so what you might want to do is just use Desmos, just draw a picture of it. R equals 1 plus cosine of theta. Okay. By the way, do you know what this is called? I don't think I've shown you this one yet. Sinusoidal is a good guess. No, it's kind of fun, especially those in medicine. Yeah, it's called a cardioid because it looks like a heart, doesn't it? Okay, it looks like a heart. So this is actually called a cardioid because it looks like a heart. And what we want to do is we want to find the length of this cardioid. Okay, kind of looks like a circle. So, by the way, as an estimate, it won't be exact. Use condenser mics with this exact pattern and sound sensitivity. Cool. Honestly, I have no idea what you're talking about because I'm not an engineer, but I believe you. It sounds cool. So this stuff is used, but in a couple of years, you'll be beyond me in terms of your work because I'm a math guy and not an engineer. But you can see, by the way, this isn't too far from a circular radius 1. Because if that were the center, it looks kind of out 1. So it shouldn't be too far from 2 pi, around 6-ish, 6, 7, somewhere like that. So it's always sometimes a good idea to just get a little visual estimate. And then at the end, we can see if it's about right. So now we need to find out, where does this start and where does this end? And again, what we can do, you can pick any point to say it starts and ends, because you can go around and end up. But the easiest point to pick is right here at the origin, because r equals 0 is so much easier than anywhere else, typically. Okay, so I'm going to pick the origin. Okay, the other choice is here, but I'm going to pick the origin where r equals 0, and let's see if we can find the theta such that r equals 0. And it won't be too bad. So let's do it. So that's the first thing, is we need to find a and b. So if I set 0, let's copy and paste this guy. I think it's the easiest. Equals 1 plus cosine theta. Then that means that the cosine of theta is equal to -1. So now, if the cosine theta is -1, what's theta? What's the first theta you know of where the cosine theta is -1? Yeah, it's going to be pi plus 2k pi is what you usually write. So in particular, if we let's say negative pi will be our first one, then the next one will be pi. So now we can say that pi, negative pi, is less than theta is less than pi. Okay, and that'll give the full cardioid. Any questions on that? And then we go and plug in. Isn't too bad. So we're going to have an integral from negative pi let's try again. Negative pi to pi. And then we're going to have a square root. We're going to have r squared, which is 1 plus cosine squared of theta. Squared. 1 plus, cosine theta, quantity squared. That's what I want. And then plus r prime squared. And r prime, derivative of r, is going to be negative sine of theta. Negative sine of theta squared, I can do that in my head. That's just sine squared theta. Any questions on this? Okay, this looks pretty nasty, doesn't it? Oops. I want to be in the equation. There we go. It looks pretty awful, but it's actually not. What is 1 plus cosine theta quantity squared plus sine squared theta? How do I simplify this inside the square root piece? Okay, and the idea is if you FOIL this out, you're going to get a cosine squared theta for your last term. Cosine squared plus sine squared is 1. We're going to have 1 for the first term, so you get 2. And then plus 2 cosine theta. This is prettier. I think I'm going to spare you the rest of it. Anyone know how to integrate this? It's kind of a mess. I think I'm not going to do it, but you could do it. You could do it using a computer on this one. Any questions on this? Any questions? Okay, in fact, maybe I'll pop it in. So it's square root of 2 plus cosine of theta. In a moment, let's see. I want an indefinite interval. There we go. From negative pi to pi. See if it even gives it to me. And take the square root. And then we have 2 plus 2 cosine. Let's call it x because it's easier. Actually, I think I have to hit cosine. Cosine of x. And then dx. See if it does it. It may give up. I think it's going to give up. Even Symbolab doesn't like it. But I wanted to kind of let you know these integrals are almost always evil. So how do you think what do you think I would do if I were to ask something like this? Oh, it does give it. What do you know? 8. Isn't that beautiful? Okay, I would ask you set up the integral. Okay, but yeah, I figured I'd show you, using a computer. Isn't that beautiful? So the length of that curve is 8. You would never guess that you look at this and it's some nice, beautiful number like 8 to walk around it, because it looks like some kind of triggy thing. But it turns out that it all goes away and it's just 8. Any questions at all on arc length? Okay, I have a question for you. And I want you to all try this. And there's more than one right answer, by the way. I want you to complete this sentence. A vector is. See if you can, without looking anything up, just off, top of your head. I want you to complete the sentence. I want you to define a vector and see if you can do it. There's more than one way of doing it. And then type in the chat box what you decide on. So a vector is magnitude and direction is one idea. Okay, there's a lot of different things you can do. Not scalar, okay. Any other thoughts? A line that starts at a point and goes forever after. Okay, usually you don't go forever after. That's what array is. So usually you start at a point and go to another point is how you would do that. Array with a specific magnitude or direction. Yeah, then it wouldn't be array. It would be, again, it would be an arrow might be the right word. Okay, the way you can say that, what you're trying to get at, when you're not realizing, is a directed line segment is what you're thinking of. So they call that a directed line segment. Okay, 2 ordered points is another way of saying it. So there are many ways of defining a vector. And now, just to be evil, next year, if you take the winter quarter course, my guess is Bruce will be teaching that, but I'm not sure. I might be. Then vector is actually going to be much deeper than you could even imagine. This may feel weird, but based on certain definitions, you are a vector. Just trust me. Okay, I know you may not feel like a vector today, but I could define it so that you're a vector. okay, as just is. But what we're going to be looking at is I'm going to add to this. Again, I wanted to be more vague, and now I'm going to be more specific. A vector in R2, because that changes things. Okay, so a vector in R2 is, and there's a lot of ways of looking at it, a directed line segment, an ordered pair of 2 points, or a point in R2, or magnitude and direction. Or 2 numbers. All of these that I just noted can be the definition of a vector. So one of the hard parts is that means anytime you talk about a vector and you have like a theorem or a property, you need to make sure you understand it for all of these different ways of talking about it. So vectors are really important because there's a lot of different ways of talking about what a vector is. Okay, next year there'll be a formal set theoretical definition, but not this year. Any questions about all these different defining definitions of a vector? Okay, and just a note, it doesn't really have to be R2. Could you have a vector in R3? What do you think? Would all of these definitions still work in R3? Instead of R2? Still 2 points, actually. Still 2 points. Yeah, they all work. How about R350? Do you think you could have a vector in R350? 350 dimensional space. Any thoughts? I don't see y'all jumping in. Sure, sure. And do you think, let's say, very high dimensional space, maybe even 1,000 dimensional space, do you think that's ever used in the real world? Where you have very large dimensional spaces all the time. And if you want to make big money, I should let you know, that's where the big money is. Do you know where? You know where the big money is right now? In terms of if you're an expert in it, you can get a job of hundreds of thousands a year. Quantum computers, nah, that's actually smaller money. AI, artificial intelligence. Yeah. So it turns out artificial intelligence is all about higher dimensional vector spaces, just to let you know, because you have many, many variables. It doesn't have to be quantum. No, quantum's completely different. Okay, they have a intersection, but they're different things. Quantum computing is pretty important, but AI is where people are going right now. Quantum computing, we're not there yet, just because computers, they're working on it. Okay, so just to note, this stuff is important. So I wanted to emphasize how important vectors are. You need to understand them. And in physics, obviously, if you're in physics, you deal with vectors all the time. So we now know what a vector is. And what we want to be able to do is we want to add 2 vectors. So arithmetic is important. Hopefully you've known that since you were in maybe first grade, that you need to add things. And whenever you have something new, you want to be able to add it. So when you're adding vectors, there's actually 2 ways of thinking about it. By the way, this picture is one way, not 2 ways. And that is, one way is the idea that you could have a directed line segment as a vector. So if you have 2 vectors, that means you have 2 directed line segments. Then what you can do is you can either take the first vector as a directed line segment and then parallel transfer the second vector so that it hits the end of the first vector, and then walk along that way and look at the triangle you get. Okay. And the vector that goes from the beginning of V to the end of W is V plus W. Any questions on that idea? The other way of doing it, which is probably even more common, is if you think of a vector as a point, and then so the vector pictorially will go from the origin to that point. So the origin is right here. And if V is this point, so it's this arrow that goes from the origin to this point, and W is this point, so it's this arrow that goes from the origin to this point. Then what you can do is you can draw the parallelogram, and V plus W will be the kind of that diagonal of the parallelogram. Any questions on the geometry of the addition of two vectors? Any questions on the picture? Where do you think this comes up in physics? Those in physics better know because it came up already for you. Where in physics does this come up? In basic physics? Yeah, adding momentum. I think even more is adding forces, but you could talk about adding momentum also. Adding momentum, adding forces, adding velocities, probably more often. Momentum can happen also. So if you have, let's say you have wind going in one direction and you have an engine that is targeted in another direction and you want to find out where you're going to end up, well, what you do is you add the vector for the wind plus the vector for the engine, and that will give you your force vector. And then you take that vector and that will tell you where we're going to end up because the force sends you in that direction. So you can think of maybe V being the wind. Well, let's call it W since wind starts with a W. So V might be the engine and W is the wind. We got a very windy day. Then V plus W will be the summation of the two forces. And that's where you're going to be pushed. Any questions on this idea? Okay, well, then there is a big theorem that comes from this picture, basically. And that is, if you look at the magnitude, so remember, vectors have lots of different defining ways of thinking about it. And magnitude and direction is another one. If you look at the magnitude of V plus W, that's always going to be less than or equal to the magnitude of V plus the magnitude of W. Why is that immediate from the picture? And you've known this since you were a small child. Not too small. Anyone know? From part A, especially. Okay, I don't see y'all jumping in, but I hope you all know this, that the closest distance between the closest path or the shortest path between any 2 points is the line segment that joins the 2 points? You better all know that, right? Shortest distance between 2 points is a line. So the vector from this point right here to this point up here is the shortest distance between the 2 points. Well, that's the magnitude of v plus w. Whereas if you decide to walk along the v path and then walk along the double path, w path, that's the magnitude of v plus the magnitude of w. And again, the shortest distance is always going to be the line segment that joins them. That's v plus w is shorter than v in magnitude plus w in magnitude. And that's what this theorem says is the shortest distance between 2 points is a line. Any questions on that? So that's the proof. You just look at it. Just a quick little definition, and this is basically the Pythagorean theorem, and that is if v now is a comma b, then the magnitude of v is the square root of a squared plus b squared. That's the distance formula. That's all that is. Any questions on that theorem? Any questions? Okay. By the way, this can't, it's a theorem kind of, but it really isn't because you can't really prove it. It's really a definition, but I think I'm not going to get into the depth of that. If you think about it a while, it's really the definition of magnitude. Okay. If you happen to have vectors as written as a number comma a number, and you want to do arithmetic, and arithmetic that we're allowed to do is addition, subtraction, and multiplication by a constant. Then the good news is it's easy. I bet you guys can tell me, without me defining it, how do you find 2v plus w? Let's see if you can do it. Give me the answer. You should be able to do it in your head, probably. So 2v plus w. So see if you can tell me how to find that. Or not how to find it, but what's the answer? Okay, good, good. So you just do what you expect to do. If you multiply by a constant of, sometimes we call that a scalar, times a vector, you're multiplying each of the components by that scalar. So that is equal to, it might be painful, but I'm going to do every step. That's going to be 4 comma 12. And then plus -1 comma 5. And then if you want to add 2 vectors, then what we do is we just add the components. 4 plus -1 is 3. And then 5 plus 12 is 17. And that's it. There's not much to it. I don't think I need to spend a lot of time on it. Hopefully you agree that that's all there is to it. What about multiplying vectors? Do you think that's just as simple and clear? Okay, and the answer is no. It's very complex. And we'll talk about that on Wednesday, by the way. But the word multiply doesn't even work. So we only add vectors, subtract vectors. We can multiply by a constant, but multiplying 2 vectors is not defined. Okay, we'll have different ways of thinking about it, though. Any questions on this example? Okay, so if V is a vector, then V is a unit vector. Let's make that in red. If the magnitude of V is 1. So I have an example. Find the unit vector in the direction of V equals 4 comma 3. Any questions on the question? So the first thing you want to do on this is cross your fingers and hope you get lucky. Maybe we just get lucky and V is a unit vector. How do we find out if V is a unit vector? How do we decide? I don't see y'all jumping in. We take its magnitude. So we look at the magnitude of 4, 3. We compute that, cross our fingers, and hope we get 1. Well, let's see. Do we get 1? What do y'all think? We have the square root of 4 squared plus 3 squared. Okay, you don't get 1, but I did try to make this one not too evil. What's the square root of 4 squared plus 3 squared? Yeah, it's 5. It's not 1, it's 5. So here's what we do. So now what we can do is we can say the unit vector, I'm going to call that U for unit. The unit vector is going to be equal to, we're going to take V and divide by the magnitude. So we're going to look at 4 divided by 5, comma, 3 divided by 5. And that'll always be a unit vector. So if you take a vector and divide by its magnitude, then you get a unit vector in the direction of that vector. Any questions on this process? Okay, now let's move to reality. 3 dimensions. So let's suppose you have R3. Okay, so again, you know what reality is, I hope. You know that we live in a 3-dimensional world. Then we want to be able to do math in our world. So one of the things is sketching by hand is really hard, but I do want to show you how to do that, even if it is hard. So let's look at 2, 1, 3, and let's see if we can sketch that. Well, by hand, meaning I'm going to use Google's drawing tool. So the first thing, just like when you sketch a point in R2, what's the first thing you do before you draw the point? What's the very first thing you do when you sketch a point in R2? Before you even touch a point? Yeah, you start with the axes. Well, we're in R3, so we're not talking about X and Y axes anymore. Now we're going to talk about X, Y, and Z axes. And there's a few ways of doing it. This is the way I like to do it. And that is, you draw this. So you draw 3 lines that are kind of equal angle, label them, and this upper one is Z. The one on the left is X. Oh, I know, I'll do it this way. And the one on the right is Y. And sometimes we call this the right-hand rule. If you take your right hand and you grab the Z-axis with your thumb, then your thumb as you curl from X to Y, your thumb always has to point to the Z-axis as you curl from X to Y, to the positive Z-axis. That's called the right-hand rule. Okay, Now we want what was it 3 comma, was it 3 comma 2 comma 1, I think. So the next thing I got to do is I need to 2 comma 1 comma 3. I was trying to remember which order I wrote them in. 2 1 3. So then I need to draw 1 2 of these. I need to draw 1 of these. And then I need 3 of these. And they should be equal distance. I'm not the best artist, but hopefully you get the idea. And then what I'm going to do is I'm going to draw the shadow. The shadow will have x coordinate 2, y coordinate 1. So if I go along the x-axis 2, and then parallel to the y-axis 1, I'm going to get this little dot. Oh, let me do it. Let me try again. One more try. There we go. I'm going to get this little dot here. Except it's not letting me. Let's try again. Whoa. Maybe I got to do it this way. Let's see if this works. Okay, that's going to be the shadow. Now I'm going to take that shadow. I'm going to walk up 3 units up the z-axis. That doesn't go all the way to here because we're starting here and we go 1, 2, 3, and it's going to be right around here. So let's draw that if it lets me. And that point right there is the point 213. Okay, artistically, it's a challenge. I'm not the best artist, but you can do it. Any questions on drawing a point? Okay, let me save it. Hopefully it works. Oh, good. Okay, now some quick things. You could have vectors, and the idea is if you have vectors in 3D, it's no different than in 2D. So I'm not going to spend a lot of time because it just means that instead of 2 coordinates, you got 3 coordinates. Often, by the way, you call them I, j, and k for the x, y, z coordinates. So if you want to go 4i plus j minus k plus 2i minus plus 5k minus 3, sorry, 2i plus 5j minus 3k, then that is going to be equal to 6i plus 6j, and then minus 4k. I figured I'd show you the IJK way of writing it. You could also write it as pointy bracket notation. Okay, and then similarly, the distance formula. The distance formula when you have x and y was just remember the square root of x1 minus x2 minus x1 squared plus y2 minus y1 squared. The distance formula for 2 points in R3, you just tag on the difference of the z coordinates squared. Any questions on that? So again, a lot of what we do in R3 is just an extension of what you've already known how to do in R2. So for example, if you want the distance between these 2 points, it's very simple. Simple, messy, but simple. You just take the square root, and then I'm going to subtract 3 minus 2 squared. 3 minus 2 is 1. 1 squared is 1. Plus, then I'm going to go 2 minus 4. 2 minus 4 is negative 2. Negative 2 squared is 4. Oops. And then we're going to go plus. And then you're going to take 4 minus negative 1. 4 minus negative 1 is 5. 5 squared is 25. And then just because it wants to, that's the square root of 30, which is not some, easy number, but it is what it is. So there's our distance between those 2 points. Any questions on that? Okay, now, as I mentioned, the first thing you learned in math, possibly in your life, was the word ball. Now we call it sphere, but same thing. And the question is, what is a sphere? Well, a sphere is a set of all points that are a certain fixed distance from a center. Well, if the center is the origin, then it's x squared plus y squared plus z squared equals r squared. And that's the sphere of radius r centered at the origin. Okay, so for example, by the way, I could go to Calcplot 3D and I could look at z equals, let's go square root. So x squared plus y squared plus z squared to the 1/2. That's the square root. Oh, wait. I forgot to do a little piece. Oh, yeah, the z's in there. Sorry. Yeah. It's getting mad. Okay, there we go. It's, if I want, say, the circle of radius 1, a sphere of radius 1, I do 1 minus x squared minus y squared to the 1/2. 1 minus x squared. Whoops. There's the minus. That's better. And there's my sphere. Now this is going to be the hemisphere because I didn't put the negative part. Any questions on a sphere? Okay, and Calcplot 3D is a lot better than Desmos, by the way, for three-dimensional plotting. Does a great job. So I recommend this one. It's connected on the syllabus. Okay, and then just a couple quick things. If you have a surface defined by x as a constant, that's just a plane perpendicular to the x-axis. And if it was y a constant, you're perpendicular to the y-axis, etc. Okay, now what about x squared plus y squared is 4? If you're not told anything about it, then you would look at x squared plus y squared is 4 and think it's a circle. Do you agree? But if we're told this is in R3 now, then it's not a circle, it's a cylinder. Because you take that circle and that will work no matter what z is, because z is not even part of this equation. Z is 10, then if you're on that circle, it's still true, which means you've taken the circle and you raised it up or dropped it down, and that'll still be part of the surface. So x squared plus y squared is 4 is going to be a cylinder of radius 2. And I can do that. There we go. And I can go x squared plus y squared equals 4. And we get our beautiful cylinder of radius 2. Any questions on the cylinder idea? And notice that it is parallel to the z-axis. If you want it parallel to the x-axis, then you change the x to a z. And now you're parallel to the x-axis because the x is missing. So it's a lot of topics today, but nothing I don't think is too deep and hard. But we're out of time. So let me stop the share and stop the recording.